Hello, everyone, and welcome to today's webinar, Simulation Showcase Urban Decarbonization Strategies, presented by IBPSA USA's EPSI Committee. My name is Ria, and I will be your moderator for today. While we wait for everyone to settle in, here is a quick rundown on what to expect. Today's session will be recorded and available through the IBPSA USA's YouTube channel. If you missed last month's simulation showcase, you can watch the recording on YouTube now. If you have any issues hearing the presentation, please try calling in by phone instead of using your computer audio. You can participate by posting questions and comments in the Q&A. At the bottom of your screen, questions will be viewable by all attendees, and there is an option to submit anonymously if you prefer. I relay your questions live to each presenter following the end of their presentation. Those of you who don't know us, we are EPSI, the Emerging Professionals and Students of IBPSA USA. EPSI is a peer group under IBPSA USA focused on professionals with less than 5 years of experience in the building performance industry. We connect early career analysts with resources, networking opportunities, and leadership insights to help you grow in your career. And we always welcome for more energy enthusiasts to join us. So please scan the QR code and join our community. I'll take a pause for everyone to scan the QR. All right, so this is the fourth installment of our webinar series, Simulation Showcase. The series highlights the work of emerging professionals and students using building simulation to tackle challenges like energy efficiency, indoor and urban thermal comfort, decarbonization, and indoor environmental quality. We invited students and early career professionals to submit their simulation-based projects. The selected participants present a 10 to 15-minute spotlight session followed by Q&A, and our reviewers will assign scores based on our review criteria. And then these three finalists will be recognized at the SimBuild conference. Today's session is this monthly series running through February, where presenters will share how simulation helped them develop real-world design solution. We can see that we do have another session coming up in February, so please do register for the workflow and tool development session. Our topic for today is urban decarbonization strategy, and we have three amazing presenters, and surprisingly, all are PhD candidates with breadth of knowledge in urban energy modeling, remote sensing, and GIS. So without any further ado, I would like to call our first presenter, Shihong Zhang. Over to you, Shihong.
Hi everyone, I'd like to share my screen now. Can I start?
Yes, go ahead.
Hi everyone, I'm Shihong Zhang from the Hong Kong University of Science and Technology. Today I'd like to talk about decarbonizing the urban buildings. So my topic will present a urban building energy modeling driven roadmap for net zero transitions in some dense cities like Hong Kong. So cities are at the front line of climate action. Especially in dense cities like Hong Kong, the buildings are the leading contributor. As we can see, buildings in Hong Kong consume about 90% of the city's electricity and contribute to about 60% of the total carbon emissions. But to deploy the large-scale retrofits, there are so many difficulties. The first one is the financial barriers, and the second one is the lack of detailed building data. So to address this issue, we developed a bottom-up and a physics-based urban building energy modeling framework, and we call it GeoBAM, which coupling the physics-based urban building energy models with detailed financial calculation. And we we modeled and simulate over 200,000 buildings in Hong Kong, and not just simplified archetypes, and these are all real buildings with its own geometry, system, and usage. To calculate the decarbonization potential, we evaluate 5 retrofit pathways for the urban decarbonization. And they are the lighting upgrades, chiller replacement, the rooftop PV deployment, the upgrades of windows and the envelope. And we not only analyze the cost benefits, but also the environmental benefits such as the energy savings and the carbon reduction. So to support the policy decision making, we calculate 5 indicators, and energy savings are and carbon reduction are as the environmental benefits. We also calculate some financial indicators such as payback period, the internal rate of return, and the market potential of each retrofit measure. So to provide a more visualization effect, we developed a digital twin platform for the urban decarbonization, and it opens to not only the government, but also the public as an interactive dashboard, and I can switch to our platform and show our platform. And we can see all the buildings in Hong Kong are located in a basic satellite image map. And if we click one building, it first shows some basic information of the buildings, such as the name of the buildings, the ID in the database, and the type of the buildings. And it will show the internal rate of return of the 5 retrofit measures. And we can see in this hotel building, the chiller retrofits achieve the best performance of investment, and the second one is the lighting upgrades. But the envelope and the window upgrades in this hotel building are not economical. Despite the financial indicators, we also calculate the energy savings and the carbon reductions. And we can see the chiller and the PV will achieve the best performance of energy savings and also the carbon reduction. And for each building, we calculate all the parameters. So in our interactive platform, it will show all the information of the decarbonization potential for all buildings. So through our analysis of our results, the quick win is the lighting, as the lighting will not only shows the highest return on investment across all building types, and it shows the fast payback period, and typically from 2 to 5 years. Especially in retail buildings in Hong Kong, the internal rate of return of the lighting retrofits can achieve about 50% due to the retail buildings rely on long operating hours. Despite and upgrading the chillers play a key role for the great stability in our results because it delivers the highest reduction in peak electricity demands, especially for the school buildings, retail buildings, industry buildings, and office buildings in Hong Kong. But it may not always have the highest return on investment. And for the rooftop PV shows, and the rooftop PV shows the huge potential for the carbon mitigation. And these two pictures shows the rooftop PV systems on 2 campus buildings in my university. And the citywide deployment of rooftop PV will achieve a reduction of carbon emissions of about 3.35 million tons. But it requires policy support because the payback period of the investment of rooftop PV often more than 11 years. And through our results, not all the retrofits are economical, such as the window replacement and the wall insulation upgrades, as the upfront investments is quite high, and the energy savings cannot recover the investment costs. So to support policymaking, we propose to unlock the green finance. If we use an investment threshold of IR at 50%, we can see the rooftop market PV in Hong Kong is very small. But if we lower the standards from 50% to 5%, the market will expand dramatically, and it will have over 25 billion market potential, and it will also unlock huge carbon emission reduction potential in Hong Kong. So for the roadmap, we propose 3 strategic steps. The first one is to prioritize the lighting and the cooling retrofits because it has the quick return on investment. And the second is we can unlock the PV market potential through some policy to lower the IRR standard. And we need also to avoid deep envelope retrofit, such as the envelope and windows in Hong Kong due to the humid and warm climate condition in Hong Kong. So finally, I'd like to thank the Research Grant Council of the Hong Kong government and my lab, the Hong Kong University Smart Building and the Construction Lab, for leading this project. Thank you very much, and I'm happy to take any questions.
Thank you so much for your presentation. It was wonderful and extremely insightful. We have a couple of questions for you. How do you calculate the urban building energy without archetype when using Energy Plus?
Through our model, we not only consider the geometry parameters, but also the non-geometry parameters. So for the geometry parameters, such as the building structure, the orientation, we get the information from the GIS data, and we can acquire GIS data through some open source platforms such as OpenStreetMap and any other sources. And for the non-geometry data, such as the thermal properties, the occupancy schedule, and operating schedules, and we collect this data from the local building standard, and we model all the detailed information in our models. And at last, we use Energy Plus to model and simulate the results.
Do you have indicators or indexes to reach energy, environmental, economic, social indexes?
As what I introduced, for the energy index, we just use energy savings, the annual electricity savings, and for the carbon reduction is similar. And for the financial indicators, we use payback period through the whole investment lifespan and the internal rate of return and the market potential, and these 3 indicators for the financial calculation.
All right, let's take one more question. About the permeability, do you vary the air change rate depending by climatic conditions?
And now we use the typical meteorological year as our climate condition input, and we modeled the air change rates. But at this stage, we refer to the building standard, but we not consider the variation of the air change rates by the climate conditions. Maybe in the future, we can consider it. Thank you.
Perfect. Thank you. I will keep an eye out for more questions, but let's move on to the next presenter for now. So we have our next presenter, Xuan Lee. Over to you, Chen.
Hi, thank you, Ria. I'm sharing the screen now. Entering one moment. Just make sure you're seeing the full screen presentation correctly.
Yes.
Okay, so hi everyone, my name is Chengxuan Li. I'm a PhD researcher in systems engineering in the Environmental Systems Lab, Cornell University. Today, I'll be presenting Energy Atlas, the tool or digital twin solution for smarter and greener cities that is developed at Environmental Systems Lab. I'll be demonstrating a case study of an urban building energy model of the city of Ithaca, New York. It simulates 5,000 buildings, etc. Let's kick off. Yeah. So cities are growing rapidly. The built environment contributes more than half of the global carbon emissions, and we're doubling our building floor area by 2060. So there's definitely urgency of decarbonization of the building stock. The built environment holds immense potential for decarbonization, we need to make cities greener, smarter, and more resilient. Urban building energy model presents itself as a great tool to support building sector decarbonization and planning for cities. At Environmental Systems Lab, we have developed a comprehensive workflow that incorporates LiDAR data, building footprints, GIS layer fusion, text assessment data, synthesis, building archetype diversification to simulate building baseline carbon emissions and plan for potential retrofit scenarios and decarbonization pathways for cities. Okay. Yeah. No. Sorry, it's slow to load. At Environmental Systems Lab, we have the. Oh no, the screen is frozen somehow. Okay. At Environmental Systems Lab, we have developed the Energy Atlas UBEM tool to facilitate data availability for UBEM use cases. We consolidate various sources of data, including building footprint, land use, and land cover, infrastructure layers, text assessment layers available at the global scale, and made them available and accessible through a viewer download the web application interface. For small-scale operations, we also introduced drone photography to reconstruct high fidelity 3D models for urban analysis and energy simulation. These digital reconstructions enable precise rooftop PV assessments, shading calculations, and facade materiality mapping. For larger scale terrain modeling and shading analysis for accurate rate irradiance simulation, we have developed a terrain voxelization workflow and ray marching algorithm to balance efficiency and accuracy and produce mass shading results for urban contexts. For the actual UBEM setup, we developed a workflow integrating LOD1 geometry, GIS layers, including text assessment, zoning, residential energy consumption survey, and commercial building energy consumption survey, and for the United States, address geocoding surveys, reference building settings, and building archetypes to create a data-enriched UBEM ready for simulation. For the UBEM archetype step, we have developed a data-driven archetype formation workflow based on the clustering result of the residential energy consumption survey and commercial building energy consumption survey of the United States microdata. We developed a method to separate building archetypes into construction archetypes, heating cooling system archetypes, and energy loads archetypes, and trained machine learning models to combine and assign these archetypes for buildings. Contrary to the established approach of doing archetypes in the urban building energy model industry, we don't do archetype building by building. We don't do prototype building models. We propose that separating them into the construction set of archetypes, including U values, air tightness, etc., the heating cooling system archetypes, including the age and efficiency of the heating cooling system, etc., and the energy loads archetype that captures the occupational occupants diversity. It is easier to decouple the user behavior from the system's efficiency and decouple the system's efficiency from the building physical parameters. With this innovative approach and the data-driven workflow of the archetype derivation and the possibility of freely combined archetypes during the assignment process, we are able to improve the initial guess UBEM simulation accuracy and produce much better results than the fixed and singular archetype of the prototype building energy model produced by the Department of Energy of the United States. We understand that archetype is a very taunting word to talk about, and assigning them is especially difficult. Sometimes you assign them to round buildings, sometimes the assignment logic works in the adverse way of what you designed it to work. So we developed this interactive tool to allow rule-based archetype assignment. It has real-time feedback, it has real-time visualization. Archetype assignment is made more easier than ever. After we have assigned archetypes, used all the GIS layer of data, we have a UBEM model ready for simulation. For the simulation pipeline, we don't use Energy Plus or equivalent software of the same level of fidelity. We believe that for larger UBEM use cases for groups of building more than 1,000, it's acceptable to have lower order models, although still physics-based, such as the 5R1C1 we are using to simulate buildings as a trade-off of efficiency and accuracy. Using historical weather, we simulate the baseline energy consumption and compare them with the actual measured energy consumption and calibrate them using an optimization algorithm called Bobby-Qua. Using Bobby-Qua algorithm, we are able to tune the input parameters for the archetypes so that the results match what we observe from the measured energy consumption data. After we have fine-tuned or calibrated the input parameters, we have a so-called calibrated baseline. With a calibrated baseline and typical weather meteorological year or typical weather data, we simulate the retrofit scenarios. For the retrofit scenarios defined for the simulation case study of Ithaca, we have defined 5 scenarios in addition to the baseline scenario that we use to calibrate the model. This includes the full electrification scenario where we swap the heating cooling equipment for the ASHP or hot water heat pumps or the ground source heat pumps, so that we call them an equipment electrification scenario. And for the second scenario, we raise all the envelopes to the IECC code so that they comply with the current code and they have much better energy consumption, energy efficiency with reduced energy consumption. For the third scenario, we combine the first 2 scenarios to simulate an ideal scenario where the building is retrofitted from bottom up. For the fourth scenario, we combine the first scenario with the PV adoption, and for the fifth scenario, we combine everything together. A quick overview of the results shows that even with only the electrification scenario, we are able to reduce 70% of the operational carbon. And for the scenarios, the fourth scenario and the fifth scenario, where we combine electrification and PV, or we combine electrification, envelope upgrades and PV, we are very close to net zero. This sounds all the way optimistic. However, there are caveats. If we look at how the PV is distributed per sector and per building, we see something that is not actually working. The analysis shows that given the promising capability of the PV adoption to support sector-wide energy self-sufficiency, even if we only install PV moderately, meaning that even we only install PV on locations of roofs with more than 1,100 kilowatt hour per year generation, we're actually very close to sector-wide self-sufficiency. However, if we broke them down to the individual building scale, the analysis still reveals a rather interesting characteristic of somewhat an uneven distribution of the PV generation potential. Under the most moderate PV adoption scenario, more than half of the buildings struggle for self-sufficiency, meaning that even if you install PV literally anywhere feasible financially, still half the buildings fail to produce enough electricity for themselves. This is somehow alarming and also indicates that install PVs on roofs anywhere would be only a part of a solution to the whole brand picture. Given the promising capability of PV adoption to support sector-wide energy self-sufficiency, even moderate deployment strategies can yield substantial benefits. If we look at the costs, if we look at the cost and the capability of the limited capability of building of the PV to support individual building level sufficiency, we see that actually it's even a better idea to adopt community incentives for PVs. So actually simulating rooftop irradiance maps or something that looks like the right bottom image is never the right way to do it. We should not only do this, but also look into potential solutions to the self-sufficiency problem of the electricity sector by introducing community PV and community solar arrays. And if we dive into if we evaluate the different retrofit incentive scenarios that affect economic feasibility, it shows that the envelope upgrades combined with electrification and especially with PV substantially improve payback performance across the building stock. While multifamily and student housing buildings frequently achieve acceptable payback periods, tree-shaded single-family housing and certain downtown mixed-use or commercial buildings, they still remain constrained by the limited retrofit programs available or the high upfront costs is eminent to the upgrade scenarios, highlighting that targeted incentives would be very crucial to this issue. We'd like to thank our team members and our external collaborators for supporting and financing this research. we have developed we have developed this energy atlas tool to be released near the end of this month at another IBPSA webinar on next Thursday. So please stay tuned and look forward to the and we can look forward to the pre-alpha release of this energy atlas tool.
Perfect. Thank you for the brilliant presentation, Chen. We have a couple of questions for you. Let me club two of them together. Is your research applicable to other cities? And the UBIM you are using is GIS based. For many cities, it's difficult to find the height. If this is missing, which data can be used?
Well, thanks for the brilliant question. So first of all, we designed this tool to be scalable. We understand that most UBIMs, or at least a majority of the UBIMs, are built bespoke for cities or bespoke for data set. We don't really want that. It's not the highest priority to only simulate the most developed cities, the most, shall we say, green cities, to decarbonize it further. We understand that it's really crucial for us as UBIM modelers or as scientists to just dream of a way, or to design our tool in a way that is applicable to the entire globe. So as the answer to the second question, we developed this, shall I say, viewer downloader tool to get footprint data, get height data, and get other relevant data for all the locations of the globe. We have this, we are working with this data source called Overture Maps. It is a map that synthesizes OSM, but OSM, we know there are locations where OSM data is not available. It synthesizes, I think, a municipal data set of Spain or something, and it synthesizes the global machine learning data footprint of Microsoft, and maybe another 3 different significant data sets. And it has global availability. It has footprint availability for the footprint data availability for the entire globe, as well as the height availability for the entire globe. And that is not very well known. That is not very well published. However, we're making this tool so that everyone can download it, everyone can view it. Maybe I think this video should show what is working on. Yeah, it's exactly what this video shows. It shows how our tool is querying the data. I don't know what is happening here, but yeah, I hope that's the answer to the question.
Yeah, perfect. Is RC model better in accuracy or efficiency compared to Energy Plus in large building energy simulation?
We are working on, shall I say, publishing a conference paper that relates to this field. But as a conclusion, I'll tell you that for monthly and annual simulations, there's barely a noticeable difference for that. For our simulations, yes, we do. However, most UBIMs, we talk about, the aggregated monthly or even annual operational carbon emissions, etc. We don't really have to care that much about hourly simulation accuracy related. So that's one side, or one part of the answer to the question. The other part of the answer question is that most of the time, the uncertainty doesn't arise from the simplistic modeling of the building physics. The uncertainty arises from the limited capability to infer the correct inputs for these models. Energy Plus can do really sophisticated models. They can simulate really accurate models if you give them accurate inputs. For UBIM applications, it's impossible for anyone to know about the heating cooling systems parameters, COPs, or vintage for every single household. So the question now is not about does our model, or does RC model, or does any reduced order physics-based model do as good as Energy Plus? The question is, can we have enough inputs so that actually the model capability matters? But actually my answer is we still lack the input. We still lack the ability to get the high fidelity building assumptions, so that to a degree where the modeling, shall I say, capability matters.
All right, let's take one last question. Solar analysis is based on QGIS use. Did you use the digital surface model? If this is missing, which data can be used?
digital surface model, I think I was wondering if you're referring to digital terrain or digital elevation or digital surface. If you're referring to digital surface, yes, it will be missing for significant parts of the world. For the USA, I think it's nationwide available. For DEMs, they are like national. They're available for the entire globe because of the availability of the satellite responses, etc. For locations without digital service model, I believe there's an article talks about the Vox City approach where they talk about how the satellite image could be used to estimate the tree canopy coverage. And if you fuse that with the overture maps and the building footprint and height, you may be able to get something that's close enough. However, I doubt that will be as perfect as we want. But for locations with a good DSM, if you're referring to DSM, for locations with a good DSM, we just need DSM to be classified, and we get the building responses, and we get the tree shading responses, and other like noise responses, and that's sufficient for our model to run to produce accurate accurate shading simulations.
Awesome. That's some great insights. Thank you, Xuan. I will keep an eye on for further questions, but let's move to our last presenter. We have Xuan Zhou.
Thank you very much.
Yeah, over to you, Xuan.
Hi. Let me share my screen. Hi everyone, I'm Xuan. I'm a PhD student in political editorial, which is in Italy, and I'm a supervisor is Professor Giulia Mutani, and I'm here to present our group research work, which is GIS-based modeling of renewable energy community. And this work is collaborate with not only the university, but also with the company like the ANA, Open Fiber, and the laboratory of RDS. And moving to our first slides, we can see that in Italy, we are facing some challenges, which we call the twin transition. The first is decarbonization, and the second is digitalization. As we all know about the decarbonization, but I would like to highlight the point of digitalization here, because the digitalization driven by AI and data centers in these years is creating a new patterns of high energy demand. And we cannot ignore that. And so to address these challenges, it starts with a high-level strategies from European Union, Great Deal, and then we go to Italian national strategies. But the point of these strategies from top to down is that how we can use that analyze at the local level. In Italy, the minimalize of the territory is primary capping. So how we can use this renewable energy community developed in our primary capping? That is the question. And our project could help to also achieve these sustainable development goals, which is about the energy, infrastructure, and also, of course, the climate. Here we can see our methodology. So in the left and also in the middle bottom, we can see here is step by step, and we start from the data collection, which is from the multi-source, and almost it's open source data set. Then we match the data to a uniform unit, which is smallest at the building level and also at the hourly. Then after create this data, we can create the job packages for the energy modeling. So we have three types of energy modeling. Start from the energy consumption and at the building scale, and also the actual production by renewable energy plants. And finally, we have the future production modeling by territories. But here we consider not only the renewable energy resources availability, but also considering the constraints which decide if we can use these renewable resources. And once we have this data, so the model will enter our platform backend to calculate the specific scenarios and also indicators, indexes. Finally, these results could be visualized on our front-end dashboard to support the decision making. And here, I would like to say it's important to realize that the energy issue are not only about the energy, but it also deeply connected to other dimensions like the economic, social, and environmental. So in the energy performance, what is most important is, as I highlight in red and also blue, it's a self-consumption and qualitative self-consumption. This is all calculated at hourly scale. This is very important for renewable energy community because the goal of a renewable energy community is to consume energy when it's produced. So it should be hourly, not daily or monthly, etc. Further, to calculate and measure the performance of a renewable energy community, we must combine a comparison of self-sufficient index, self-consumption index, and overproduction index. Because once you want to get high self-consumption, but it shouldn't be you also have a very high overproduction because it wastes a lot of energy produced. So this is about our indicators and indexes framework. So here I'm going to show in the following our results of our simulation by our platform. So first, we can say about the energy consumption in Italy. As we can see here, we have a lot of consumed energy in industrial. It's almost half of total. And on the bottom, you can see here is hourly profile of the residential energy profile, and also for services, industry, and also agriculture. So we can see different peak on the hourly profile, and this is very important because it allows us to mix different user type within a renewable energy community to balance our production and consumption to maximize the self-consumption. And here is a map of the actual renewable resources production existing in Italy. So we can see here the hydropower is the main sources used in Italy, accounting of about 29% of total. So also we can say the distribution of the renewable resources we use now. In Italy, we mainly use the hydropower in the mountain of Alpi, and also the solar is mainly in the cities because the solar technology we use in Italy is mainly based on the roof. And also the wind is because of the distribution of the wind velocity. So it's mainly in the south and also the islands. But also I want to highlight that the biomass. So the biomass we use in Italy is not only like the agricultural forest, but we also use the waste to energy. So that's why you can see in the north where you can see a lot of the purples. There is Milan and also large cities like the Venice and also Turin. It's all we can produce a lot of waste to energy. So, but at all, let's say if we're comparing to the future potential, we can say that we still have a lot of renewable resources we can use, especially for solar. Because when we're evaluating the future potential, we can say the result shows that the solar produced as much more higher than our resources. So here, the solar energy is depends on the territory. So it's abundant in the south and also islands, but it's peaking during the day and the summer. But however, the wind energy in Italy, which is also strong in the south and islands, but it peaks during the night and the winter. So if we're comparing or if we want to mix the renewable energy resources use, this is also critical to understand how we can mix our renewable resources. And on the bottom, you can see that here we have a lot of constraints based on renewable energy sources. Because if you want to turn this potential into a reality, it's limited by some regulation. It's not only European Union regulation, but also in Italy, we have a lot of culture sites to protect. As you can see here is an example, which is in my city of Turin. Here we have a lot of solar radiation, which we can use on the roof, but not all roofs could be installed photovoltaic, because here we have a lot of historical buildings and also culture buildings. Here we have an example which is in the center of this city. Here we have a historical center which is called Porta Nova. This is the train station. So also on the wall we cannot install photovoltaic offshore. So this is constraints considering renewable energy resources. And here, once we get all data, so now we can go to the backend. So our backend architecture designed specifically for speed and also dynamic, which allow you to update your data, like if you have a new consumption or if you install the new renewable resources plans. So it's allow you to update this data via API. And the core of this backend architecture is that we use the materialized view, which is to pre-calculate and the complex data join. So the result shows if we directly ask some queries, some data, it will take more than 2 minutes. And after this 5-layer backend structure, it reduced to 0.01 seconds. So this is also very important for the front-end users, because if you want to do some integration with this platform, it should be as fast as they can. And here we can say we simulated different scenarios from baseline scenario, which is 0, and to the future scenarios considering one of the maximum use of renewable resources. So this one is the solar, and this 2 is wind. The 3 is about biomass, and 4 and 5 is about energy sharing. And 4 is residential, 100% residential sharing with other sectors, while 5 is about owning part of which is 25% of residential users share the energy with only residential sectors. And the 6 is also, as we can see, the biggest map. It's the maximum we can get from renewable energy resources in Italy. Okay, so as we can see, as a baseline scenario, it's almost red, which means we have a very low self-sufficient and a lot of uncovered demand energy. And when we do some renewable energy community, like the energy sharing, so we can say we improved a lot of self-sufficient. While if we go to the maximum potential of renewable energy community in Italy, we can say that almost 65% of municipalities in Italy it reaches almost enough self-sufficient. Okay, so let's move to the implementation. So we're considering the scale of aggregation if you want to develop the renewable energy community. So our model also allows us to look at the energy communities to renewable energy territories. As we can see maps at the bottom of the Piedmont region, which is the region of where is Turin. We can see here from red, generally we get the more higher self-sufficient. And also, I want to show you on the top is that in large cities, how our modeling performance or how the renewable energy community performance. We can say that in Milan, even it's the maximum potential, but we still have a very low self-sufficient indexes, which is the government or the decision maker need to be considered if they can move their industrial, like as we know, we have a lot of data centers around Milano. Milan, there is a big, huge energy consumption already. So maybe they could considering give some policies or give some incentives to move their biggest energy consumed infrastructure. And finally, here we can go to the front end, which is based on the stakeholders. So every stakeholders could have a different permission to do the analyze. And here we can see example of Milan. Here, if you access the front end, we can show the hourly profile, the energy consumption profile by sector. And also we can say what is the actual energy production and also the scenarios you could choose. But as we can see here in the bottom of this slides, all users could choose the amount of the renewable energy they want to install, such as if we consider maximum it's 100 per 100, but if we considering like reduced a little because in the maximum scenarios we have a lot of overproduction. So if we consider like the 50% solar coverage, so maybe the platform could automatically calculate the all indicators we discussed earlier, such as self-sufficient, self-consumption, and also the payback time, which you installed, how much years you can get your money back. And this is very important to do the dynamic analyze and also the radiance analyze for a national energy system. To conclude, our research highlights the importance of the twin transition, and also here on the top of these slides, you can see a lot of scenarios we analyzed, we simulated, as we discussed the scenario 6, although it can reach its largest self-sufficient, but we still have a lot of overproduction and also a low self-sufficient self-consumption indexes. So therefore, based on our analysis, based on our scenarios simulated, it is recommended the energy sharing scenarios like scenario 4 and 5, which is you could share your energy, also the mixed use by sector copying. So by integrating device the loads like the residential, commercial, industrial, and also agriculture, we could create a more stable and also efficiency system. So this is the whole context about our platform. It could turn data into action and also driving to a more sustainable future for Italy. And also in the future, it could be used for other countries, not only in Italy or not only in Europe. It could use in any context. So thank you.
Thank you for the great presentation. We have a couple of questions for you as well. Is your work publicly available as of now, and who will be the target user for the platform?
Could you repeat it again?
Is your work currently available right now publicly?
Okay.
And who is the target user for the platform?
I could like say start from the policymaker in the government because they need to develop the renewable energy community in their territories. So like if you are the policymaker in Milan, you want to compare with what is your level in maybe in the middle or the median of your region. And also you need to consider how much is your benefit you can get from your policies. And then we could like to enhance the users like the energy company, which also could be use this platform to evaluate, okay, if they are going to investment here, or if they want to move their data centers, how much benefits they could get from their decision making. This is a decision making platform. So also I would like to say this is also built it for everyone, let's say, especially for citizens, because as we discussed, this simulation modeling is building level. So for everyone, they could check their renewable energy resources used situation in their municipality and also on their districts. And if they're considering to develop the small group renewable energy community based on their primary cabins, so they need to discuss as a member.
Yeah, Is this a GIS-based tool? How you manage future scenarios considering, for example, climate change?
Yes, this is, let me go to in the front. Yes, this is the GIS-based model. Everyone is calculated in GIS because we create the packages and then we go to the Beaver, go to the PostGIS database. So for the energy modeling, for the for example, for future production modeling, like for solar, firstly we use the DSM optimeter of Italy and also DTM in Italy because in some region we don't have the DSM, and then we evaluate the solar radiation by ArcGIS and also QGIS, some solar simulation tool, and then we go to the building boundary. We create the solar radiation on the roof, and then we choose the technology in Italy as we show here. So we select one technology we will use for the renewable energy analyze. And then we could calculate the production. And also it's GIS based for consumption because this farm work or this methodology is top to down. It's not based on building simulation. So we get some data from regional or the national government statistic data, and then we distribute this data because this is real data, it's not simulated data, and then we distribute the data from regional to province, and to province to municipal, and then to the district, and then to the building scale. It's based on also statistic like for example, for residential, we need to consider number of families. We need to consider the building volume. But while if we consider industry, we need to consider if we can get the number of employees, and also we need to considering how much the peak hour, the peak of energy, the science contracts there. So this is all about the energy use, and we need to convert this data considering how we can use it in QGIS and how we can merge or manage this data at national scale. This is the main idea of this GIS-based modeling.
Yeah. One last question. Are there economic incentives for renewable energy communities as of now,
Until now, the incentives for created renewable energy community, what we developed in our analyze is only this. So is only this how much energy you could sell to the network is only this. We haven't considering other incentives yet, but in the future we can aid because now we have the farm work. So because now we have the farm work, once we want to calculate any of the policies, indicators, it's just we ask for data. It's just write a formula and then it can calculate it as soon as it could.
Perfect. Thank you so much, Xuan. This was a really great presentation. Let me just quickly share my screen. Before we wrap, a big thank you to our presenters. We hope this was a great platform for your projects, and we are so glad IBPSA-USA could give you this platform to showcase your work. And thanks to our audience for supporting our students and emerging professionals along the way. We got more projects and events coming up, so make sure to check out IBPSA-USA website for what's next. We also have a Career Connections event coming up. I'll just post a link in the chat if you want to register. The deadline for early bird registration is very close for exhibitors. Please register and join us meeting employers and getting interacted with industry professionals down the line. And don't forget to subscribe to our channel. We have a YouTube channel and you can catch today's recording over there, explore our webinars too. Thank you everyone once again and have a wonderful rest of your day.